Sound like a breaker or something.
Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Tuesday, our second happiest day of the week. We have been talking about relativity, and we most recently have been looking at space-time intervals. So delta S squared is c delta t squared minus delta x squared minus delta y squared minus delta z squared. We're starting to look at relativistic linear momentum, relativistic kinetic energy, rest energy, total energy, and kind of a connection between energy and momentum and rest energy. So I'll give you the following. Relativistic momentum goes as m times u over 1 minus u squared over c squared under the radical. This is sometimes written as equaling gamma u mu. And what I will caution is to note that I've subscripted this gamma. This looks a lot like the other gamma that we were using, right? But remember that the other gamma that we were using, it wasn't 1 minus u squared over c squared under the radical. It was 1 minus v squared over c squared. The difference being that v was the relative velocity between the two reference frames that we're measuring something. This is something that you're looking at within your own reference frame. So you're watching something move, you want to ascribe a momentum measurement to it, and the relativistic linear momentum goes as m times u divided by the square root of 1 minus u squared over c squared, where u is actually the magnitude of this velocity that you measure for the thing. So that's okay? All right, so then relativistic kinetic energy goes as quantity gamma minus 1 end quantity times mc squared. We will, it's also gamma u, by the way, but we'll go through in lecture, we'll look at this and we'll see that for slow speeds, this really does turn into half mu squared. So, but that is only true where u is much, much less than c. Is that also all right? We're going to take a look at that in lecture when we actually take a shot at deriving that, so, or at least justifying it. One of the things that pops out of this is this idea of rest energy, that in some sense mass is a form of congealed energy, or that mass and energy are at least two different interpretations of the same thing, right? So, or that mass is just another form of energy. The trade-in value of mass to energy is mc squared. This is E equals mc squared, probably the most famous equation out there. So remember that in special relativity we're not allowing acceleration of the frame, and so the kinetic energy plus the rest energy, that's all she wrote. That's all there is. And if I take gamma minus 1 mc squared and I add mc squared to it, that's gamma minus 1 plus 1 mc squared is just gamma mc squared is the total energy. So if I take this and add it to this, I get this. Yeah? One last nice thing that will give us a shortcut to a lot of the problems that we're going to attempt over the next couple days is this. It's the E squared equals PC quantity squared plus MC squared quantity squared. And so with that, let's see if we can try a few somewhat quick problems. And I apologize, I am keeping this a little short this week. I have a meeting starting in about half an hour. So cathode ray tube. If this used to be like a really straightforward example, but if you've ever seen an old TV set or computer monitor, right? This used to be something everyone was familiar with, but less so in today's world. This is a cathode ray tube display. Effectively, there is a little gun back here that is accelerating and firing very, very high speed electrons. They're going to be steered with a magnetic field so that they trace back and forth and raster back and forth across the screen to light up pixels. But the thing that we're talking about is just the cathode ray part, the thing that's firing the electrons at high speeds. And so in this problem, we have a cathode ray tube that is firing electrons with a speed of 1/4 the speed of light. We want to know what the kinetic energy is. And so here, we can just plug and chug style problem. The kinetic energy is just gamma minus 1 mc squared. And so if we plug in our values here, we can well, there's a couple ways we can do this. I guess in my notes I took the long tour here. So let's do this as I did this in my notes, just to give a little more familiarity with these equations. So the total energy is going to be gamma mc squared. I've given you here a few of our standard bearer particles: proton, neutron, electron. The mass of the electron in units of mega electron volts per c squared is 0.511. And so we could say 1/1 minus 0.25 squared times 0.511 times 10 to the 6 EV over c squared, and then times c squared. What nice thing happens here? Note c squared and 1/c squareds cancel, and we get 0.511 times 10 to the 6 electron volts over 1 minus 1/4 squared is 1/16. So this is 0.511 times 10 to the 6 electron volts over the square root of 15/16. I'm going to cheat. I'm going to say that this winds up being about 0.528. I don't have to cheat that calculator. So 0.511 mega electron volts. 15 divided by 16 square rooted, shift 1/x, times 0.511 is about 0.528 mega electron volts.
That is total energy, but
That's the total energy.
we're looking for kinetic energy.
And so if we want kinetic energy, so one thing that we can see from this is that E total is KE plus ER. And so KE is E total minus ER. And so the kinetic energy should be our 0.528 mega electron volts minus the rest energy, which is 0.511 mega electron volts. And so and that is about 0.0168. That's probably too many sig figs. MeV. Okay.
We said that the electron volt is just a unit.
Yeah. So the electron volt is just a unit of energy.
Okay.
And so, it's 1.6 times 10 to the minus 19 joules. Yay? So far, so good.
So far, so good, Professor.
Okay. Then let's try another problem. This time with a proton. This time we're told that the total energy of a proton is 3 times its rest energy, and we want to determine what the speed of said proton is. And so, so this time we could say that the total energy, gamma mc squared, is equal to 3ER. We can write this as gamma mc squared is equal to 3 mc squared.
Because the R is MC squared.
And so the mc squareds go away, right? And so we can say that 3 is equal to 1, and this is gamma u, right? This is why I cautioned you at the very start that we're using gamma u's here, because I'm not going to remember to subscript them. So,
So every time we talk about momentum, it's gamma u.
or the total energy or the kinetic energy. So, is that all right? So, so we have 3 is equal to gamma u, right? And so we can square across. 9 minus 9 u squared over c squared is equal to 1. We can say 8 is equal to 9 u squared over c squared. We'd say 8/9 is equal 8/9 c squared is equal to u squared, or u is equal to the square root of 8 over 9. Is about 0.943 c. Which that in a way that I like. So I'm getting, I don't know, in my notes for some reason I also did this as meters per second, and I'm getting about 283 million meters per second. But 0.943C is also true. So. Yay?
Yep, fantastic.
Awesome. If we wanted to find the kinetic energy, then there is kind of a straightforward approach here. Kinetic energy is going to go as gamma u minus 1 mc squared. But what do we know about gamma here?
Gamma is the one we calculated.
So we said that gamma was 3. And so 3 minus 1 is going to be 2 mc squared. Since if this is m, and it's 938.28 MeV per c squared, if I take m times c squared, what do I get? I get 938.28 MeV.
Maybe, yeah.
So 2 times 938.28 MeV is 1876.56 MeV. And in my notes, I rounded it to 1880. Is that all right?
So we have the rest mass given in MeV for convenience for this kind of problems.
Yep. So we could turn this into kilograms, but it winds up being easier to leave it written in terms of energy per c squared.
So we can cancel this square
So
right
that
away.
when you multiply stuff by c squared, which is quite common, you're left with something in energy. So if we want to find the momentum, here we can use that equation at the bottom. We can say that E squared is equal to PC squared plus MC squared squared.
P is for momentum, correct?
P is for momentum. And so here we know the total
Energy.
the total energy is 3 times the rest energy. So this should be, let me know. I have space, so let me use it. So let's say 3ER squared is equal to PC squared plus ER squared.
Because MC is just ER.
And so, yeah, MC squared is just ER, right? So this just winds up being 9 ER squared minus ER squared is equal to PC squared is 8 ER squared is equal to PC squared. Yay? And so we can see that the momentum.
Shouldn't be the P squared as well, since.
Oh, yeah. Thank you. I dropped my parentheses. It's not a good idea. That P squared is 8 ER over ER squared over C squared, or that P is equal to root 8 ER over C. And so we could say this is root 8 times 938.28 MeV over C. I got, let's see, 2650, give or take. MeV over C is a unit of momentum. Mega electron volt per speed of light. Is that all right?
So you went from AER squared over 0 squared to P equals...
So then I square rooted both sides, and 8 to square root 8 ER over C quantity squared rooted is ER over C.
Oh, okay.
And then ER is just MC squared,
Yes.
but that's just 938.28 mega electron volts divided by C.
You said those are the units of momentum? Right?
Yep, those are perfectly valid units of momentum.
Fantastic.
Okay, so speaking of momentum, if you have missed the days since Physics 130 when you did conservation of momentum problems, well, you're in luck because we're still doing conservation of momentum problems. It's just this time we're talking about high enough speeds that we can't use the approximation that momentum is just m times u. This time it needs to be gamma times m times u, gamma u. So what we have in this version of the problem is an electron traveling at some unknown speed, u, is that, let's call it u sub e, collides head-on with a neutron traveling at 0.60 C. After they collide, we see that the two particles are at rest. And so the question is, what speed before the collision did the electron have in order for them to both be observed at rest afterwards? And as I already gave away, this is a momentum problem. And so after the collision, what's the momentum? Just 0. And if we believe in conservation of momentum, then the momentum before the collision also had to be 0. So if we say that that after P total equals 0, then before they collide, P total had to be 0. The only way that can be true is if the magnitude of the momentum of the electron is equivalent to the magnitude of the momentum of the neutron. They're traveling in opposite directions. Let's say the positive direction is to your right. The electron has positive momentum, the neutron has negative momentum, but they add to 0.
Oh, okay.
So their magnitudes needed to be equal so that the positive and the negative add to 0. Yay?
That's the only way we'll add to 0, right?
That's the only way we can get this to add to 0. So now is just some tedious algebra. So we are going to say that the neutron, m neutron, u neutron, in magnitude, over 1 minus u neutron squared over c squared has to equal m electron, u electron over 1 minus u electron squared over c squared. So far, so good.
So far, so good, Professor.
We could square both sides. It's the route I took in my notes. So let's take 939.57 MeV per c squared times and squared 0.6 c quantity squared over 1 minus 0.6 squared. That's the neutron, yeah? Notice that that we could get we could simplify this a little by stealing a c squared from this to get rid of one of the c squareds from this. I'm not going to bother with that for now. Mass of the electron squared 0.511 mega electron volts per c squared times this unknown UE squared is 1 minus UE squared over c squared.
We're looking for UE, correct?
And we want to find UE. And so we can multiply across and let's see. Let's figure out what this thing on the left is, because that one we can do pretty completely. So 939.57 squared times 0.6 times 0.6, and then divided by 0.64. Is 496,570. I'm gonna be really bad in, what is that, MEV squared over C squared? MEV squared over c to the 4 times c squared. I think that's right, yeah?
That looks right to me.
So then we can say that 1 minus UE squared over c squared is equal to 0.511 MEV over c squared times UE squared over 496,570 MEV squared over c squared. And so, let's see, shift 1 over x times 0.511 times 0.511. I'm getting about 5.26 times 10 to the minus 7. 5.258. We'll leave it at this. Times 10 to the minus 7. And that is let's see, that is per c squared. Does that work? Which we could write like that. Okay? Since this is equal to this, I can bring like terms to one side, and we get that 1 is equal to u e squared over c squared times 1 plus 5.26 times 10 to the minus 7. Does that make sense? So I think that's right. It's at least what I got when I did this in my notes. So then I can move things to the other side, and I can say that that UE is going to be 1 plus 5.26 times 10 to the minus 7 to the half, to the minus half, right, divide across, and then times c squared, times c, because I'm square rooting. And so we can use our binomial approximation, 1 plus x to the minus half is approximately 1 plus minus x over 2. Yes, I can write that as 1 minus x over 2. And so we could say that this is approximately, we'll cheat pretty liberally here, 1 minus 2.63 times 10 to the minus 7, about half of that, times c. So you can see that this is very, very close to the speed of light. Right? If we wanted to try this classically, then we still would say that the momentum magnitude of the electron would be the same as the magnitude of the neutron's momentum initially. And so we would say that that ME UE needs to equal MN UN, or that UE would just be MN over ME times UN. And 939.57 over 0.511 times 0.6 C winds up being 939.57 divided by 0.511 times 0.6 is about 1103 C. Note that if we did this classically, the electron would have to travel about 1100 times the speed of light for this to work. But if we do this relativistically, what we see is that the speed of the electron is very close to the speed of light, but it's still slightly smaller, right? So
The classic is wrong.
So this is not the approach to take. So for very, very, very high speeds, we need to take this approach. Is that okay?
Is there an approximate speed at which this will stop working? Like diode went
No,
off?
but you can kind of check with gamma, right? If you plugged in, let's look at gamma u, right? It's 1 over 1 minus u squared over c squared under the radical. Let's look if we were at 1/10 of the speed of light. So this would be, so gamma u equals 0.1 c. This would be 1 over 1 minus 1/10 squared is 100th. So this is 1 over root 0.99, right? That is about 1.005. So at this point, things start to differ by about 0.5%. 0.5%. Is that enough that you care? I don't know. If you were to double the speed, right? 0.2 squared is 0.04, and so this becomes 1 over the square root of 0.96, right? And so that's about 1.02. So that's about 2%. I would say at that point, that's 2% is kind of noticeable, right?
Yeah.
So it kind of depends on what your tolerance is for how close is close enough. But I'll also tell you that, 1/10 of the speed of light is really fast. That's 300,000 meters per second, or it's about 18,600 miles per second. So at 1/10 of the speed of light, gamma is still close to 1. So, all right, I gotta run to my meeting. As always, you guys are awesome. Have wonderful days. Thanks for stopping by. Don't be strangers. Enjoy your days without so much. We'll see you next time.